Hello everyone, and welcome to today's webinar. Let's discuss catheter balloon technologies, manufacturing, processing, and testing. Before we get started, I would like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you would prefer to join over the telephone, just select phone call in the audio pane, and the dial-in information will be displayed. All attendees are in listen-only mode. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation, and we will collect these and address them during the Q&A sessions after each presentation. Today's webinar is being recorded. And with that, I would now like to introduce Tony Kuda, Regional Sales Director, Machine Solutions, our moderator for today. Go ahead, Tony.
Hello, and welcome to the next webinar in the Machine Solutions series of online training webinars. These webinars are designed to provide insight on the technology and techniques behind Machine Solutions equipment and processes that we support. Today's webinar is called Let's Discuss Catheter Balloon Equipment. This consists of three topics: balloon manufacturing, balloons processing, and testing of balloons. My name is Tony Kuda, and I'm a Regional Sales Director for Machine Solutions, and I work with our Balloons and Testing Solutions groups. As Machine Solutions continues to integrate the most respected brands of catheter manufacturing and testing equipment into the Machine Solutions family, we strive to be the one-stop shop for industry-leading manufacturing equipment, testing equipment, and services to the catheter manufacturing industry. Today, we have three experts here to provide insight on different topics surrounding balloon development. These topics are balloon forming, which will be presented by Rudy Altorfer from BW-TEC, balloon pleating and folding, which will be presented by Brian Strani, CEO of Machine Solutions, and a balloon testing overview, which will be presented by Christina King from Crescent Design. Let's get started. Rudy Altorfer is our BW-TEC sales leader. BW-TEC manufactures several different types of equipment, including several platforms of BFMs or balloon forming machines. These are used to produce balloons for angioplasty and other medical applications. He'll be presenting on the following: extrusions, basics, and necking, machine selection, and balloon processing and molds. After his presentation, we will take questions, so please enter any questions into your question block. Now let's go to Rudy.
First of all, greetings from Switzerland, and thank you for attending the webinar. Balloon forming is not only science, but a combination of art and science, and it involves a lot of research and development. What are the key ingredients associated with creating a repeatable balloon forming process? Because in the end, we want to have a good quality balloon. Key ingredients. We need a good extrusion. We need a repeatable necking. We need a good quality mold, as well as a developed balloon form recipe on a stable equipment. Let's look at some of the ingredients in more detail. Preliminary process. Extrusion, that's the raw material, and we need a good raw material to work with. If extrusion is not good, then the whole process can't help to make a good quality balloon. So extrusion is key. We always say extrusion makes up to 70 or 80% of the whole process. It's a key ingredient. So we need a good supplier, a supplier that can deliver on a consistent basis, consistent quality, and a supplier that allows to work with that we can make quick adjustments to the extrusion during the development phase. Because we know a change of supplier is difficult. Again, consistency. Quality, good and long-term supply with consistent material characteristics, and quality is a key to produce high quality balloons. The next thing that we are looking in a good extrusion is elongation. The elongation of the extrusion is key for forming a good balloon. For a semi-compliant PTCA balloon, for example, it should be at least 300%. The elongation can and should be tested for each batch in cold conditions. Then let's go to the next process step, the necking process. The necking process is a preliminary step in the balloon forming process, and it describes the forming of a parison by necking down the sleeves to a defined diameter. What is a parison/slug? A parison is the part of the raw tubing that is not necked down and out of which the balloon is formed. So we see that on the slide. We have the extrusion, the raw tubing, then the parison, and out of the parison we form the balloon. Why do we need a parison? Often a parison is needed to fit the necked part of the tube into the balloon mold, since the tube diameter is bigger than the sleeve diameter of the mold. With a parison, we define where the balloon will be formed and how much material is needed for the forming process. So with a parison, we have control over the process, and a parison increases the stability and repeatability of the process, which has an effect of the quality of the balloon. Another important advantage, a parison helps to pull the material through the cones and is critical to achieve the desired wall thickness in the balloon as well as in the cones. The necking process makes the sleeves more rigid, which ensures that when the stretch is done in the forming process, the pulling happens only in the balloon and not on the whole tube. We have, again, therefore, more control. BW-TEC recommends using a parison for the forming process for a balloon bigger than 2.5 millimeters. The bigger and longer the balloon becomes, the more important a parison is. A defined neck and consistency of the parison length are the two most important things to look for in a parison. Another thing that we can do is to inspect the parison before we bring it into the balloon forming machine. So inspecting the neck before forming a balloon can be beneficial. We can look for stars, air pockets. For the R&D phase, a good starting point is that the parison length should contain about 70% of the balloon length. That's a starting point, and from there we can define what the parison length needs to be. Machine selections. What are the differences between the necking machine that BW-TEC offers, and what are the pros and cons? Our brand new machine that we see in the slide, the 2920 split die necking machine, has a servo motor included. We made a new design of the clamp for more centricity, and we have a digital readout of the parison. So the slug length is a process parameter in the HMI. With that, we have more process control and it's easier for validation. This machine can do 0.7 and up to 10 millimeter in tube diameter. So basically the whole range that we need for all kinds of different balloons. The next machine that I want to present is our 5-up necker, the 2105. This machine has the core process or the core technology as a hot air system. This one is especially made for high volume for PTCA dimensions, so from diameter 0.4 to 3.5 millimeters. Forming process. Let's go to the forming process. We need to offset the parison in the mold. The parison must be really centered in the mold before the forming process. Different materials need different temperatures and time for the material to be soft and ready for the pulling process. This is probably the most important step in the forming process, giving the material enough time and not try to make a shortcut in that process step. the material needs to be ready to jump, to form a balloon. It needs to be ready for the stretch. The recipe steps that are laid out in the BW-TEC machines are: first, we increase the temperature, the time we leave, we give the machine the time, we give the temperature the time, the material the time to soften. Then we stretch, we pull on the tube, and then again, we increase the pressure for the next forming step. One thing that is key in the forming process: the forming of the balloon should be done at the same time as the stretching is happening. Even if we have on the distal and the proximal side, we have a different pulling speed or pulling distance, the timing should be at the same time. We have here in the slide a diagram of the forming process of a BW-TEC equipment. So the first, we see pressure. The next in the chart is the temperature, and the third is the position. So we increase the pressure, then we increase the temperature and give the material time for the forming. And then we make the stretch. As we can see in the blue frame, everything should be at the same time. So we see a pressure drop, which indicates that we have a balloon. And on the positioning, we see it's done at the same time as we have done the stretch. On the BW-TEC equipment, we have the option for flow feedback and force feedback. The flow feedback or the flow measurement shows how much airflow is in the tube. This is an additional indicator of the forming of the balloon. This is especially important and helpful and useful in the R&D phase, but also on the production floor. The same is true for the force measurement or force feedback. It records the force on the extrusion during the process and provides important feedback for optimal process development. As we can see here in the blue frame again, we have the feedback in the chart that we have the pressure drop, the pulling, the force, and the flow at the same time, which is a good indicator that we have a forming of the balloon. Again, machine selection when it comes to the balloon forming machine. The BW-TEC equipment allows the stabilization of the balloon as a recipe parameter to prevent shrinkage of the balloon. Different balloons machines for different requirements. We have different elongations, we have different forming pressure, we have the ability of pump during the forming process, and of course the design of the balloon has an influence of the machine selection. This machine or standard machine, the 50-55 1-to-4 up primary secondary concept, allows you to make the whole range of balloons from 1.5 to 40 millimeters in diameter and 10 to 350 millimeters in balloon length. The vertical concept convinces that we save floor space, that we can start with a primary machine, and we can gradually add secondary machines. So up to 3 secondary machines can be added to one primary machine. And one operator can operate 4 machines at the same time. The other machine that I want to highlight is our brand new balloon forming machine for soft balloons, for PU materials with a high compliant balloons, soft balloons. The concept convinces with a split mold, which allows almost unlimited possibilities of shapes and designs when it comes to the mold. And the machine impresses with short process time, pulsation ability in the forming time. Mold selection. The mold has, of course, and for obvious reasons, a huge influence when it comes to the forming of a good quality balloon. BW-TEC produces a variety of high quality balloons mold for a wide range of applications for the medical field. Our machine shop is equipped with modern equipment to meet the highest customer demands in terms of quality, design, and manufacturing tolerances. So what are some known types of challenges when it comes to the art of balloon forming? Again, we come back to the extrusion. Even minor climatical changes such as temperature, humidity, thermal radiation, and altitude can have an influence on extrusion and thus on the molding process. The shelf life is important. A fresh extrusion and a couple of days old one might show different specs, which has an influence on the forming process. Even different batch can have an influence on the forming process. Another thing that we see often that we don't take enough time to find a balanced recipe. So a balanced process parameters are key for consistency and high yield. Taking the time during the R&D phase to develop a recipe that is designed in such a way that minor differences in the extrusion, different batch and so on, still allows a good quality balloon. Heating blocks. The correct size of a heating block that fits the mold, not too loose, too much process time for the heating and the cooling process. So here it's worthwhile to invest in maybe one more heating block. On the other hand, we save time on the process floor. BW-TEC recommends refurbishing the heating blocks every 2 to 3 years so that the heating and the cooling functions do not decrease. That's another thing that is often forgotten when it comes to the challenges in the forming process. So again, thank you so much for attending the webinar. And if you have any questions, please feel free to ask. We would be delighted to answer them. Thank you.
Thanks, Rudy. Let's go ahead and take a few questions that we've gotten here. The first question is, what is the relationship ratio between the diameter of the extrusion and the diameter of the balloon?
Sorry, Rudy, you are muted. Go ahead and click on the icon in the top left corner. There you go.
Okay, sorry about that. Thank you so much for the question. That's not an easy one. It's a good question, but not an easy one. And it's difficult to make a general statement because it's very material and product dependent. But for a PTCA or a small PTA size balloon, the following can be said as a guideline. The max balloon OD is max 5 times the tube ID.
Okay. The next question we have is, what's included in the refurbishing of the heating block and what does that affect again?
So, I mean, the heating block, if we refurbish the heating blocks are completely disassembled. We clean them of possible lime and deposits, and we fit them with new heating cartridges as well as insulation. After that, the heating blocks are, of course, tested. We make a test protocol, and we send that to the customer. And with that, basically, the heating block is almost brand new. It has the same performance again as a new one.
Okay. And the last one we'll go with here is it possible to open different user accounts with different permission levels on the machines?
Yep, Yeah, that is possible. So within the HMI, you can give different levels, different access and permissions levels. You can also, and that might be interesting for some of our customers, you can also offer, or make set range in the process parameters in which the operator can adjust the input and to apply to the characteristics of the extrusion.
Okay, well, thank you for your presentation. Next, we will be discussing balloon pleating and folding with Brian Strini. Brian is a CEO of Machine Solutions, and early in his career with Machine Solutions, he was the product manager for MSI Pleat and Fold product lines. He was and continues to be an integral in the development of several of our current platforms and technologies that make Machine Solutions the industry leader for this critical manufacturing process. Again, please enter any questions into your question block. Now let's go to Brian.
Thank you, Tony, and thank you all for attending our webinar. My name is Brian Strini, and I am going to discuss pleating and folding. So we're going to take a high-level look at the application, the machine types, and the pleat head designs. So from an application side of things, the pleat and fold process creates equal sections or pleats of a balloon. So you take an inflated balloon, place it into the pleat head then closes and creates those pleats. Typically, we're looking at between 2 to 8 pleats, and that is really dictated by the inflated balloon's diameter. Those pleats are then folded around the catheter shaft utilizing the fold head, and you can also apply thermal energy throughout the process from the pleat or fold head, which can help to create the pleats and also influence rewrap characteristics. So what are we trying to gain out of this process? Well, we need it to be accurate and repeatable. We do not want any backfolding or unwanted creases in the pleats that could lead to a larger OD or a non-uniform expansion of the balloon. So again, those even pleats are going to provide us with that uniform expansion if it's just a straight angioplasty procedure, or if there's a stent placed on top of that balloon, it is going to allow that stent to be deployed uniformly. And the outcome that we want from the process, again, accurate and repeatable, but with that key characteristic being that folded OD. So we want that outside diameter of that folded balloon to be the same unit after unit with that smallest possible crossing profile. And then on top of that, if you're crimping a stent, that folded balloon OD is going to dictate your overall stent crimped OD. So machine selection, we have 2 basic types of machines, a pneumatic and servo. The pneumatic systems are going to utilize cylinders and air pressure to open and close the heads, and mechanical hard stops to control diameter. The pressure can be adjusted by the user to apply various amounts of force on the pleat or fold side, and the hard stops can also be adjusted to create different closed diameters for the fold head or open diameters for the pleat head. On a servo controlled system, we're utilizing servo motors that will create that motion on the pleat and fold heads and encoders for diameter control. Also, there's typically a load cell integrated into the activation system, which allows us to monitor force that the heads are applying throughout the process. Within that servo family, we also offer an eye system. And what the eye system allows you to do is to utilize the pleat and fold head simultaneously throughout the process so that you're utilizing or using both heads at the same time rather than a traditional approach of pleating and then folding. So what that affords the operator is an increased throughput because you're not waiting on one head to finish to start the next process. The other 2 types of machines can be configured as a tabletop or a workstation, either of which can carry different types of pleat heads. But the key difference with the workstation is it allows you to have multiple heads on a single platform that are already calibrated and already up to temp. So if you're varying your balloon sizes throughout a day or a production run, the machine is ready to go as simple as scanning a barcode or calling up the recipe. The machine then knows which head to utilize. Conversely, if you're doing a tabletop machine that has a single pleat or fold head and you need to switch sizes throughout the day, You're going to install a different pleat head, calibrate it, and then warm it up to whatever operating temperature that you have selected. We also offer film systems, and these machines utilize an integrated layer of film that's laced through the head, and it's protecting the balloon surface from the steel elements either in the pleat or fold side. And so this allows you to protect that polymer, that drug, from being damaged in the pleat fold process, or potentially cross-contaminating throughout the day if some of that coating would come off on an element and then be transferred to a subsequent balloon. So pleat head design. So there's some main design parameters that we look at whenever we're designing a pleat head. The main ones here are the pleat direction, the number of pleats, the balloon length, the min or max inflated balloon diameters, the closed diameter of the head, and then the wing gaps. And all of these design parameters that go into the elements, we look at the largest of the matrix to make sure that we're not damaging the balloon. If the wing gap or closed diameter is too small, you could pinch the balloon and create some pinholes or damage in that balloon. So we're always looking at the largest parameters to design to ensure that we have no issues with pinching or adverse effects throughout that process. And all these parameters are developed from the MSI balloon information sheet, which will be provided early on in the assessment process to the customer to fill out. So this is an example of the BIS and the different categories or parameters that we look to collect, and it can go upwards of 4 or more balloons depending on what the user needs to pleat and fold within their matrix. So this is typically detailed early in the process. It allows our engineering team to take a look at it and understand what number of pleats would be best suited for this application, lengths of heads, diameters, and some of those general parameters that really feed the design process. So we're going to dive into each one of these a little bit further. So first, we're looking at the pleat direction. So we typically look at it from the proximal end of the balloon and the direction that those pleats are then formed, either counterclockwise or clockwise. And that's a user-defined parameter. As we look at number of pleats, we offer between 2 and 8 pleats, and that is more on our engineering team's discretion to recommend a certain amount of pleats based on the overall balloon characteristics or parameters. 2 pleats, typically, a 2 millimeter, 3 millimeter balloon, we might do a 2 pleat. When you get up into some of the larger diameters, 20 plus millimeters, we're going to look to utilize an 8 pleat. And then head diameter and head length. We offer various lengths of heads from 60 to 350 millimeters in various increments, and open diameters between 2 and 40 millimeters. We can go larger than 40 millimeters if needed, but that range of 2 to 40 is where we see most of the applications landing. Inflated balloon diameter range. So as a general rule of thumb, one pleat head may be able to process a range of about 2 to 1. So for example, 2 to 4 millimeters, 6 to 12. And what we're looking at there is that holds true if the marker band and distal seal diameters are the same or similar. And what we're looking at in that area is if your largest distal seal is, let's say, 40 thou, and your smallest is 20 thou, and you're trying to run that in one single pleat head, that smaller diameter distal seal won't necessarily center every time directly in the center of that 40 thou opening, closed diameter opening. So we want to make sure that the delta between the smallest and largest diameters, either distal seal or marker band, are close enough that we are confident that the balloons on the smaller end of that range are going to center correctly and not create a shorter or longer pleat, which could lead to a non-uniform fold and deployment. We also have to make sure that the head opens wide enough to accommodate the largest pressurized balloon in that range. And then these final two pieces, the element wing gap and pleat radius, those are intertwined. And what we're looking at there is the element wing gap, the length of it has to accommodate the balloon material at the largest diameter. So if you look at the top 2 images there, you can see how the 2 millimeter balloon extends about a third up that wing gap, whereas the 4 millimeter balloon goes pretty close to the end. The lower image there shows a balloon that's too large for that given pleat design, and it's actually extending past the end of the wing gap. And what that can do is it can create a backfold in that section. And if it goes too far past the end of the wing gap, it can actually be pinched by the hard stops between the elements and create a pinhole or some damage to the balloon. So when we look at sizing, if that balloon material is going too long up to the wing gap, what we would typically do is go to a higher number of pleats, so that pleat length is shorter. But then what that might do on your lower end of your balloon diameters is create a pleat that's very short. And that can be difficult to lie down in the right direction as it's folded repeatably. And that can lead to a backfold in that smaller pleat. The other area that we can look at is making the overall wing length longer, but typically the design that has to be created there, the angle at which the pleat leaves the root has to become a little bit straighter to allow that length of the wing gap to be longer. And as you straighten that section out, that shorter pleat in your smaller diameter balloons may not have that proper radius or geometry imparted in it, and again can lead to backfolding or bunching of the balloon in those smaller diameters. So we talked about closed diameter a little bit on the previous slide. So this is a good example of what we're actually talking about. And it's the through hole that is seen as all the elements are closed down. So it's the diameter that's tangent to the elements at full close, that red arrow that you see across there. And so as we look at the distal seal or marker band diameter, whichever is greater, we want to make sure that diameter through the closed diameter can accommodate those various sizes without pinching. If we land that tip of the element into the distal seal because it's too large for the closed diameter, it'll create witness marks or potential damage. And if the marker band plus double wall thickness is our largest diameter and we close down, the marker band can be pinched between the balloon material can be pinched between the element tip and the marker band, and again, potentially create damage in the balloon. So wing gap, another critical parameter for repeatable and optimal performance. Again, this comes from the balloon information sheet, and it's the distance between the two wing areas when the elements are at full close. That small red arrow you see about a third of the way up that left wing gap. And that design parameter is based around the thickness, the double wall thickness of the balloon. And typically what we see is that double wall thickness can be the greatest in that taper section of the balloon. So make sure as you're reporting that measurement that you're taking into consideration that taper thickness. So when we design this, we want to be able to close the pleat head as tightly as we can to that double wall thickness to create a very uniform and non-wrinkled pleat. But at the same time, we don't want to overclose and pinch that balloon material. So that concludes a high-level look at the process, the equipment, and the pleat head design. So we'll look to have questions at this point.
Thanks, Brian. Yeah, we had a few questions come in. Let's start with, is the closed diameter of the pleat head variable?
Okay, that's a good question. So typically the closed diameter of the pleat head is not variable, and it's fixed in relation to the full close of the head. However, there are applications where we can vary the closed diameter to be slightly larger than a nominal, but this needs to be evaluated by our engineering team.
Okay. The next one we're going to go to is, are the systems able to process sub-assemblies rather than full catheters?
Sure. Yeah, our FFS systems can be configured with various types of lure connectors or tube connectors. So as long as we're able to hold pressure or vacuum in the balloon, we're able to process catheters or raw balloons of various types.
Okay, and the last one we're going to do, can you exchange pleat and fold heads between machine bases and platforms?
Yes, yeah, definitely. Pleat and fold heads of the same length can be exchanged between machine bases that have the same or similar or the same activation systems, being pneumatic or servo. And then we also have models like the Workstation and 475, 575 that can handle a limited range of pleat and fold head lengths. So they definitely can be exchanged between machine bases.
Great, thanks for all that information. That's a really good topic to go through. Our final topic today will be an overview of balloons testing. Christina King from Crescent Design is our value stream leader for our testing products. She's an industry expert in balloons testing and has been with Crescent for over 25 years. Christina will be discussing important topics that pertain to balloons testing. Again, please enter any of your questions in the question block and we can go to Christina now.
Thanks, Tony, and thank you everybody for joining us today. My name is Christina King, and in the 25 plus years that I spent with Crescent Design, I've learned all the ins and outs of our hydraulic burst leak tester, as well as supporting customers to help develop tests for their products. The focus today is on catheter balloon testing. So I'm going to be discussing burst testing, leak testing, fatigue testing, and compliance testing. First, I'd like to discuss why we do testing. Testing provides us with valuable information about our catheter balloon's performance, as well as its safety for use in the field. Testing is also required for regulatory compliance. ISO 10555 specifies a variety of ways in which intravascular catheters need to be tested for use in the field. Testing allows us to determine the failure characteristics of our products. It's important to know at what pressure the balloon or catheter fails and where and how does the catheter fail. In a production environment, acceptable quality limit testing is required. A percentage of every batch of catheters must pass certain test criteria in order for that lot of balloons to be released to market. And we also do testing during the R&D and design assurance phases of developing our balloons and catheters. Burst testing is the pressurization of a balloon or balloon catheter until it fails. Bursts are characterized by a dramatic change in pressure over a short period of time. It's important to use the right tool or piece of equipment to get a job done accurately and correctly. And selecting a burst tester is no different. Some things we want to consider in our selection are things such as, does the tester have a maximum pressure great enough to detect burst events? Do we have adequate deliverable volume for testing? And are the resolution and accuracy good enough to meet our testing requirements? Burst test parameters to consider when we're developing a burst test include our ramp rate, target pressure, and burst rate. When we're selecting our ramp rate, it's usually dependent on the type of product that we're testing, as well as maximizing our test time. For instance, if we're testing a catheter with a very small lumen, we're going to need to select a slower ramp rate due to flow restriction. If we're testing a catheter that is more compliant and larger, we can go faster with our ramp rate, but we do need to be careful not to go too fast as to lose control of the ramp. We should set our target pressure higher than the pressure that we expect our product to fail. And the burst rate should be set in order to trigger burst conditions. Leak testing is more complex and is dependent on the size of the leak and the compliance of the whole catheter. For instance, a cardiac catheter is non-compliant compared to an esophageal catheter. And this is going to affect how our leak test is designed. Leak detection can only take place during the dwell period in a program tester script. The HBLT must stop maintaining pressure in order to detect a change in pressure that would indicate a leak. When we're selecting our leak tester, we want to consider similar things to our selection of a burst tester, but the resolution and accuracy are much more critical to leak testing. Leak testing parameters include what pressurization mode are we going to use. Typically, a leak test is done in a staircase pressurization mode, where we need to indicate an initial pressure, an increment pressure, and a maximum pressure. Our maintain and dwell times are very important in leak testing. We want to have a maintain time that's long enough that the catheter has an opportunity to settle at the target pressure before stopping and dwelling to look for leaks. We want to set our leak rate and our leak dip in such a way that it will trigger events when the product fails. Fatigue testing involves ramping the catheter to a target pressure for a programmed number of cycles. Fatigue testing may include both leak and burst detection, and with a smart manifold, fatigue testing can be performed on up to 10 products at a time. This can be done automatically and unattended by an operator. Fatigue test parameters include target pressure, return pressure, burst rates, maintain and dwell time, leak rate and leak dip, and the number of cycles. ISO 10555 Annex B provides us with a good example of a simple fatigue test. The standard calls for a balloon to be pressurized to its rated burst pressure and maintained there for 30 seconds for a total of 9 cycles. Our target pressure in this example would be the rated burst pressure. Our return pressure would most likely be 0, and our maintain time is 30 seconds. Compliance testing involves diameter measurement or dimensional verification of pressurized catheters in a temperature-controlled water bath. Measurements may be single point or multi-point along the length of the balloon. With a position control system, customers can measure the length of the balloon, find the center of the balloon, and the largest diameter of the balloons. It can also be used to take proximal, medial, and distal measurements of the balloon. MSI has chosen to use an optical micrometer because it has demonstrated the ability to detect the edges of the balloon in water. Some catheter balloon materials' refractive index is close to that of water, and the Keyence optical micrometer is able to detect those where we have found the laser micrometers cannot. People often ask me why hydraulic pressure testing. So I'd like to go over that a little bit here. The biggest benefit or reason for testing hydraulically is that balloons and catheters are pressurized hydraulically in the field. And if our product handles liquid, it should be tested using liquid. Product failures during testing will be representative of actual failures in the field hydraulically. Another reason is for regulatory compliance. ISO 10555 calls for liquid leakage under pressure. Hydraulic testing tends to be more sensitive than pneumatic testing, and very small changes in volume result in large pressure changes, making leak detection more sensitive. Last but not least is safety. Water is incompressible. There is no stored energy, and therefore the pressure returns to 0 almost instantaneously after an event. I've included some images here of 2 raw balloons, two balloons that are exactly the same but tested differently. The top balloon was tested hydraulically with our HBLT. The balloon below was tested pneumatically with an indeflator. I think the photos speak for themselves. However, both products had a similar failure, a similar burst pressure, but you can see that the failure mode is very different. I've talked a lot today about testing products, what parameters to use, which leads me to something that we call product characterization. Product characterization is the process of trying different test settings and parameters that will produce the most accurate, efficient, and repeatable test results for a specific product. Things to consider with characterization include the compliance of the product. Is it a rigid product or is it a compliant product? What pressurization mode do we want to use? I've mentioned today several different modes. Leak, burst, and fatigue testing typically use different pressurization modes. We want to select a correct maintain and dwell time. What are our units of measure? The HBLT allows us to select PSI, atmospheres, bars, and kilopascals. And then what model pressure tester do we want to use? The HBLT is available in models that have a maximum pressure ranging from 25 PSI all the way to 5,000 PSI. And there are reasons for using different models. What are the consequences of not characterizing our product? These things include false events, undetected failures, test settings or parameters that do not produce the same results from one machine to another because they are not optimized. And when we don't get repeatable and reliable results, the quality of our products can be called into question and could lead to product recalls. Pressure Manager is a great tool for doing product characterization. It allows us to see the pressure and volume graph in real time. And with sensitive enough settings, we're able to dial in the correct compliance and burst and leak criteria in order to get the repeatable results that we're after. The two graphs that you see here represent the same product tested prior to characterization and then after being properly characterized. The graph on the left, for the graph on the left, the compliance was set too high, which caused the ramp rate to become increasingly unstable. The customer set the burst and leak detection too low in order to ignore this instability in the ramp to achieve a target pressure. However, this led to undetected failures as well as test results that did not match from one machine to another. With the use of Pressure Manager and trying different compliance settings and different burst and leak criteria, our engineers were able to achieve the graph that you see on the right. We see a very stable ramp rate, and we got repeatable burst criteria over several different samples. So I think this example really illustrates the importance of doing product characterization. That's all I have for testing today. I really appreciate your time and hope that you learned something. Please feel free to reach out to MSI to learn more about or ask questions about our services as well as our testing equipment. Thank you so much and have a great day.
Thanks, Christina. Douglas Preston is our testing lab technician. He'll be taking some questions pertaining to catheter testing. We have a couple of them here that we're going to go through. Doug, what is the compliance setting? Can you talk a little bit about that?
Yeah, the compliance setting is essentially the gain setting that tells the HBLT how much give or flex your product and text fixturing has. This is what allows the HBLT to achieve its smooth pressure ramp. This is completely different from a compliance test where you test pressure versus diameter directly.
Okay, and the last one we're going to do here is, how do you save the data from a test?
Well, with an HBLT by itself, it essentially just gives you a pass or fail based on the test criteria that were specified. A dot matrix printer connected to an HBLT will print more detailed information. However, to get the raw data from a test, you need to use Pressure Manager, and what you'll get is essentially a CSV that contains the pressure over time from the test you ran.
Okay, thank you. Thanks for the presentation and all the information. That concludes our webinar today, and thank you to everyone that attended. You will be receiving a follow-up email with a link to the materials presented, and we will try to answer as many of the follow-up questions as we can for you. Also, we'd like to thank all of you that took the time to learn more about balloon manufacturing, processing, and testing. We hope there are takeaways for each of you, and welcome discussing additional questions at your convenience. Thank you again for attending, and have a fantastic day.